On September 24, 2023, a small capsule descended through Earth's atmosphere above the Utah desert, trailing a brilliant fireball across the sky. Inside that approximately 250 grams of material collected from the surface of asteroid Bennu, some 200 million miles away. For most observers, this might have seemed a modest payload hardly worth the expense and effort of a multi-billion-dollar space mission. But to the scientific community, the contents of that capsule represented something far more profound. Direct physical evidence of events that occurred billions of years before Earth itself formed, preserved in pristine condition, and now available for intensive study in laboratories around the world. This was the culmination of the OSIRIS-REx, origins, spectroscopy, imaging, and mass spectrometry to study the origin of carbonaceous asteroids and the evolution of the Sun mission, one of humanity's most ambitious scientific endeavors. Launched in September 2016 from Cape Canaveral, the spacecraft had traveled through the vacuum of space for over 2 years just to reach its target. It then spent nearly two additional years studying the asteroid from orbit, mapping its surface in unprecedented detail, and planning an extraordinarily delicate maneuver to collect samples from this ancient object. The mission represents far more than a simple robotic retrieval operation. It embodies humanity's evolving relationship with space exploration, our ability to ask sophisticated questions about our cosmic origins, and our capacity to design systems capable of answering those questions with remarkable precision. The importance of the OSIRIS-REx mission extends well beyond the immediate scientific findings, though those findings are themselves extraordinary. This mission marks a fundamental shift in how humanity approaches planetary science. For centuries, astronomers and scientists were confined to passive observation. We could study distant objects only by analyzing the light they reflected or emitted. We built increasingly sophisticated telescopes, developed spectroscopy to analyze chemical composition from afar, and constructed mathematical models to interpret what we saw from Earth. But all of this was inherently limited. We were studying the universe through a distant window, unable to physically interact with the objects we sought to understand. The OSIRIS mission represents humanity's transition into an era, direct contact at an age in which we can dispatch robotic emissaries to distant worlds, collect physical samples, and bring them home for detailed analysis under controlled laboratory conditions. This capability opens entirely new domains of scientific inquiry. It allows us to answer questions that were previously inaccessible to us. Most importantly, for the context of the Bennu mission, it allows us to study the actual chemical and physical properties that formed in the early solar system before being significantly altered by planetary processes or atmospheric exposure. Understanding why scientists considered asteroid Bennu such an important target requires stepping back and considering what we actually know about the formation of our solar system. And significant gaps remain in that knowledge. The standard model of solar system formation tells us that our Sun and its retinue of planets formed approximately 4.6 billion years ago from a massive cloud of gas and dust known as the solar nebula. This collapsed under its own gravity, eventually forming the Sun at its center. The remaining material in the disk around the Sun underwent a complex series of collisions and gravitational interactions that eventually led to the formation of the planets we know today. However, this seemingly straightforward narrative encompasses tremendous complexity and remains incompletely understood. The exact sequence of events, the timescales involved, the role of different chemical processes, and the mechanisms by which planets acquired their distinctive characteristics are all subjects of active scientific research and considerable debate. Scientists seeking to understand these processes a fundamental challenge. The geological record of these early solar system processes is extremely fragmentary. Earth, as the oldest terrestrial planet and the focus of most geological study, has been extensively modified by internal geological processes, atmospheric weathering, and biological activity over the past 4.5 billion years. The earliest rocks in Earth's crust have been metamorphosed and altered to the point where their original characteristics are often obscured. This is where meteorites become invaluable. Meteorites represent samples of solar system material that have been preserved in a relatively pristine state since the early solar system. Many of them formed at the same time as Earth and contain within their mineral structure a record of the chemical and physical conditions that existed during planetary formation. However, meteorites have their own significant limitations as samples. When a meteorite falls through Earth's atmosphere, it experiences tremendous heating due to friction with the air. This heating can alter or destroy delicate chemical structures. After landing, the meteorite sits exposed to Earth's weather, rain, wind, dust, and biological contamination for an unknown period before being discovered and collected. By the time a meteor reaches a laboratory, it has already been compromised as a sample of pristine solar system material. This is precisely why the OSIRIS mission was designed with such singular focus, to retrieve a sample of carbonaceous asteroid material that had never been exposed to Earth's atmosphere, never beaten by atmospheric friction, never been altered to weathering processes or biological contamination. Scientists needed a pristine sample, a window into the early solar system that had not been obscured by the intervening billions of years of terrestrial alteration. The target. Why Bennu was chosen. The selection of asteroid Bennu, officially designated 1955 Bennu, as the target for the OSIRIS-REx mission, was not made arbitrarily. NASA scientists and mission planners applied rigorous criteria to identify an asteroid would serve the scientific objectives, while also being accessible to a spacecraft and amenable to sample collection. Bennu is a near-Earth asteroid, meaning its orbital path brings it relatively close to Earth at regular intervals. The asteroid follows an elliptical orbit around the Sun with a semi-major axis of approximately 1.126 astronomical units, placing its average distance from the Sun slightly beyond Earth's orbital distance. At its closest approach to the Sun, called perihelion, Bennu comes within approximately 0.90 astronomical units of the Sun, a distance slightly less than Earth's orbital distance. This orbital geometry means that Bennu periodically crosses Earth's orbital path, bringing it into a region of space that a spacecraft launched from Earth can reach with manageable fuel requirements. The asteroid itself is relatively modest in size, with a mean diameter of approximately 490 meters. While this might seem large, in the context of asteroids, Bennu is actually quite small. This size range is ideal for mission planning. An asteroid that is too large presents challenges for orbital operations and sample collection. An asteroid that is too small might not have retained the materials scientists wanted to study. Bennu's size falls into what proved to be an ideal range for the technological capabilities of the OSIRIS-REx spacecraft. However, the most significant factor in Bennu's selection was its spectroscopic classification. Asteroids are classified into different types based on how they reflect sunlight at different wavelengths, their spectral signature. The vast majority of asteroids fall into two main categories: S-type asteroids, which are primarily composed of minerals and metallic iron, and M-type asteroids, which are primarily metallic. These asteroids represent the debris from collisions among planetary bodies in the asteroid belt and other regions of the solar system. They have been significantly altered by heating, gravitational compression, and differentiation, the process by denser materials sink toward the center of a body while lighter materials float toward the surface. B-type asteroids, by contrast, are much rarer and represent a fundamentally different category of material. B-type asteroids are carbonaceous, meaning they contain a significant fraction of carbon compounds. They are dark, reflecting very little of the sun's light. Most importantly, for scientific purposes, B-type asteroids are believed to preserve material from the earliest stages of solar system formation, material that has been minimally altered since the solar nebula first began to coalesce. If S-type and M-type asteroids represent processed and differentiated remnants of planetary formation, B-type asteroids represent the raw, primordial construction materials. They are the bricks and cement left over from building the solar system, preserved in their nearly original condition. Bennu is a B-type carbonaceous asteroid, which placed it in an extremely desirable category for the mission's scientific objectives. Scientists were not simply interested in any asteroid. They specifically wanted to study material that preserved a record of the early solar system in its most primitive, unaltered state. Bennu's classification indicated that it was likely to contain precisely such material. The mission designers also recognized that bringing back a sample of carbonaceous asteroid material was particularly important because such material is statistically rare among the meteorites found on Earth. This rarity might be due to several factors. Carbonaceous meteorites might be more fragile and break up more completely during atmospheric entry. They might be less easily recognized or collected, or the population of meteorites that falls to Earth might not be a representative sample of all asteroid types. Regardless of the reason for their rarity in terrestrial collections, obtaining a pristine sample of carbonaceous asteroid material directly from the source provides scientists with material that was essentially unavailable through traditional meteorite hunting. The orbital dynamics of Bennu also played a crucial role in the selection decision. While Bennu's orbit brings it relatively close to Earth, it is also gradually changing over time. Calculations indicated that Bennu's orbit is slowly evolving, and there was a window of opportunity during which a spacecraft reach the asteroid, study it, collect samples, and return to Earth. This window would not remain open indefinitely. The mission planners recognized if they were going to take advantage of the opportunity to visit Bennu and return pristine samples to Earth, the time to do so was relatively limited. This urgency, combined with the scientific value of carbonaceous asteroid material and the orbital characteristics of Bennu, made it the ideal target for the OSIRIS-REx mission. Mission design and architecture. The OSIRIS-REx spacecraft was engineered as a sophisticated robotic explorer, combining elements of orbiters, rovers, and sample return spacecraft. The design had to balance numerous competing requirements. The spacecraft needed to be capable of traveling to a distant asteroid, entering into orbit around it, performing detailed scientific observations, collecting samples without contaminating them, and then returning to Earth with those samples intact. Each of these requirements presented distinct engineering challenges, and the solutions to those challenges had to work together in a coherent system. The spacecraft itself, relatively modest in size compared to some NASA missions, with a total launch mass of approximately 2,110 kilograms. This relatively lightweight design was intentional. The spacecraft needed to be launched on a commercially available rocket, in this case, an Atlas V rocket, and needed to carry enough fuel to perform orbital maneuvers around Bennu, hover over the asteroid's surface, and perform a complex gravity assist around Earth to return to the home planet. Using a smaller, lighter spacecraft made these maneuvers more fuel efficient and therefore more feasible with the available launch vehicles and budgets. The spacecraft's design incorporated several distinct functional modules. The main body of the spacecraft houses instruments for remote sensing and analysis, the computers and communication systems, the fuel propulsion systems, and the various subsystems necessary for spacecraft operations. Extending from the main body is a long boom, essentially a mechanical arm, that reaches out to collect samples from the asteroid's surface. This boom was topped with a specialized collection head called a touch-and-go sample acquisition mechanism, or TAGSAM. The TAGSAM head was one of the most critical and innovative components of the entire spacecraft. It was designed to perform an extraordinarily delicate task: to touch down on the asteroid's surface, collect a sample of loose material without being damaged by rocks or bouncing off the surface, and then retract to the spacecraft. The TAGSAM head resembled an inverted car air filter about 30 centimeters in diameter, attached to the end of a long spring-loaded arm. The collection strategy was ingenious in its simplicity. Rather than trying to excavate material from the asteroid or use complex mechanical means to gather samples, the TAGSAM system was designed to use a puff of pressurized nitrogen gas. When the collection head touched down on the asteroid's surface, compressed nitrogen gas would be expelled downward, fluidizing and agitating the surface material. This puff of gas would send dust and small rocks into the air, and the inverted funnel design of the collection head would direct this material into collection chambers. The material would then be sealed and stored until the spacecraft could return to Earth. This design reflected a sophisticated understanding of the physics of asteroid surfaces and the behavior of granular material in low-gravity environments. On an asteroid with only a tiny fraction of Earth's surface gravity, traditional excavation methods would be ineffective. A mechanical scoop or drill would have difficulty gripping material that wants to float away. The nitrogen puff method, by contrast, worked with the properties of the asteroid environment rather than against them. It was elegant, efficient, and relatively simple critical considerations for a robotic system that would operate billions of miles away from Earth with only limited ability to troubleshoot problems or make repairs. The spacecraft also carried a comprehensive suite of scientific instruments designed to study Bennu from orbit before and after the sample collection maneuver. These instruments included cameras operating at different wavelengths, a thermal infrared spectrometer to measure the temperature and composition of the surface, a laser altimeter to map the three-dimensional surface topology, and a magnetometer to detect any residual magnetic fields associated with the asteroid. Together, these instruments provided scientists with detailed information about Bennu's surface properties, composition, temperature, and physical characteristics. The spacecraft was also equipped with a sophisticated guidance and navigation system. Unlike Earth, where GPS satellites provide continuous location information, a spacecraft in deep space determines its own position and orientation through a combination of measurements. The OSIRIS-REx spacecraft used optical navigation, meaning it took images of recognizable stars and features on the asteroid to determine its location and orientation. This system had to be extraordinarily precise. Errors in position or orientation could result in missing the asteroid entirely. Worse, crashing into it at high speed. The journey to Bennu, the OSIRIS spacecraft launched from Cape Canaveral on September 8, 2016, atop an Atlas V rocket. After achieving Earth orbit, the spacecraft performed a series of maneuvers that gradually increased its orbital energy, lifting it onto a trajectory that would eventually intersect with Bennu's orbit around the Sun. This journey required patience. The spacecraft did not travel in a straight line to Bennu. Instead, it followed a long, gradually expanding trajectory, using its rocket engines to incrementally boost its orbital energy over the course of months. The journey from Earth to Bennu took approximately 2 years. On December 2018, more than 2 years after launching from Earth, the OSIRIS-REx spacecraft finally arrived at Bennu, matching the asteroid's orbital velocity and beginning to orbit it. This moment represented the culmination of years of planning, engineering, and mission preparation. However, arrival at Bennu brought a surprise that would reshape the remainder of the mission. Scientists and mission planners had predicted what they would find when they arrived at Bennu based on observations made from Earth-based telescopes. Thermal models constructed from these observations suggested that Bennu's surface should be covered in fine-grained sand, a regolith similar to what had been found on other asteroids studied by previous missions. Scientists envisioned landing sites that were relatively smooth, with gentle slopes and an overall sandy appearance. These predictions were based on the best available data, but they proved to be significantly inaccurate. When the OSIRIS-REx cameras first imaged Bennu's surface at close range, scientists and mission engineers were confronted with an unexpected reality. Rather than a landscape of sand and gentle slopes, Bennu presented a chaotic terrain of massive boulders. Some of these rocks measured dozens of meters across enormous obstacles on an asteroid where the overall surface gravity was minute. The surface was rough, jagged, and chaotic. There were no obvious landing sites, no smooth patches of regolith suitable for sample collection. Instead of the sandy beaches that mission planners had anticipated, OSIRIS-REx at what appeared to be a construction site disaster. A landscape of broken rock piled upon broken rock. This discovery sent shockwaves through the mission planning team. The TAGSEM collection mechanism had been designed and tested with the assumption that it would be operating in a relatively benign environment with fine regolith and no large obstacles. The safety protocols for the spacecraft's maneuvers had been calculated based on models of a sandy asteroid. The presence of the enormous boulder field presented serious concerns about the safety of attempting the collection maneuver. If the spacecraft descended into this rocky terrain, there was a genuine risk that it could strike one of the large boulders and damaged or destroyed. However, this crisis in mission planning also brought valuable scientific discoveries. Multiple observations from the spacecraft revealed something unexpected and fascinating. The surface of Bennu was not stable. On several occasions, the spacecraft's cameras captured images, jets of rocky particles erupting from the surface. These particles were being ejected from Bennu with enough velocity that some of them escaped into space, never to return. Others followed brief orbital trajectories before falling back to the surface. This phenomenon, known as particle ejection or outgassing, had never been observed to such a degree on an asteroid before. It provided a crucial clue to understanding Bennu's fundamental nature. The presence of these particle jets, combined with other observations, led scientists to conclude Bennu, what astronomers call a rubble pile asteroid, rather than being a monolithic, solid rock like the bedrock beneath our feet on Earth. Bennu is essentially a loosely aggregated collection of gravel and rocky debris held together only by the asteroid's own weak gravity. The asteroid is not a cohesive object like a planet or moon. Instead, it is more like a floating pile of rubble, barely clinging together in the vacuum of space. This conclusion was supported by careful measurements of Bennu's density. Solid rock on Earth typically has a density of approximately 3,000 kilograms per cubic meter. Measurements of Bennu's mass combined with estimates of its volume based on imaging yielded a density of only about 1,190 kilograms per cubic meter. This remarkably low density meant approximately 50% of Bennu's volume is empty space void vacuum. The asteroid is roughly half composed of nothing at all. If Bennu were rotated just slightly faster, the centrifugal force from that rotation would overcome the asteroid's weak gravity, and the entire structure would drift apart into a dispersing cloud of dust and debris. Understanding Bennu's rubble pile nature completely changed the context for mission planning. Rather than descending onto a relatively stable surface, the TAGSAM collection attempt would be occurring on a loose, unstable pile of rocks held together by the faintest gravity. This realization simultaneously increased the dangers and increased the importance of careful planning. However, also provided insights into why Bennu's surface looked so chaotic. Rubble pile asteroids are inherently unstable. Rocks sit on top of other rocks, balanced precariously. The weak gravity means there is minimal force holding material in place. The slightest disturbance could cause rocks to shift or tumble. Over billions of years, this constant instability would create exactly the kind of chaotic, jagged terrain that OSIRIS-REx had imaged. Mapping and site selection fit the landscape far more challenging than anticipated. The mission team had to completely reassess the feasibility of collecting a sample from Bennu. However, the scientific value of the mission was too great to abandon. Instead, mission planners and engineers wondered one of the most detailed remote surveys of an asteroid's surface ever conducted. Over approximately 2 years in orbit around Bennu, the OSIRIS-REx spacecraft carried out an exhaustive mapping campaign, imaging the asteroid from multiple angles, at multiple resolutions, and under varying lighting conditions. The spacecraft used its cameras and instruments to build up an extraordinarily detailed three-dimensional model of Bennu's surface. Every major boulder identified and catalogued. Slopes and surface irregularities were measured. Thermal characteristics were analyzed. Scientists looked for locations that might be suitable for the TAGSAM collection attempt places, where the surface might be less chaotic, where there were fewer large boulders, where the slope was not too steep. This search was extraordinarily challenging. The spacecraft was orbiting a small asteroid, only a few hundred meters in diameter, while carrying delicate instruments and maintaining precise control of its position. Every orbit of Bennu brought OSIRIS-REx back over the same ground, but the lighting conditions changed, providing new perspectives on the surface features. Scientists gradually built up a comprehensive understanding of the brain, looking for locations that might be feasible sites for the collection attempt. Eventually, a potential landing site was identified. A small crater on Bennu's surface designated Nightingale. This crater, measuring approximately 20 meters in diameter, appeared to offer some advantages compared to other locations. The crater was relatively small and narrow, and its walls appeared to contain areas where there might be finer-grained material mixed among the boulders. Most importantly, the crater appeared to be just barely wide enough for the OSIRIS-REx spacecraft to descend without its solar panels striking the crater walls. The margins for error were extremely tight, but Nightingale appeared to be best available option for collecting a sample. Mission planners developed an extraordinarily detailed operational plan for the sample collection attempt. The spacecraft would approach the crater, descending slowly and carefully into its interior. Throughout the descent, the spacecraft's cameras would monitor the approaching surface, and the guidance system would make adjustments to the trajectory to ensure that the solar panels cleared the crater walls. The descent would continue until the TAGSAM collection head was within a meter or two of the surface. At that point, the collection sequence would commence. The nitrogen gas would be expelled, the surface material would be fluidized and drawn into the collection head, and the spacecraft would immediately begin backing away and rising out of the crater. The entire collection operation planned to last no more than a few seconds. The spacecraft descend and retreat so quickly that there would be minimal risk of the spacecraft becoming entangled with surface feeders or losing control of its position. Every detail was planned and replanned. Engineers and scientists conducted extensive simulations of the operation, practicing the maneuvers in software models that incorporated the detailed topography of Nightingale Crater. The goal was to be as prepared as possible for an operation that would be conducted millions of miles away from Earth, where there was no possibility of immediate human intervention if something went wrong. The sample collection, October 20 on October 20, 2020. More than 4 years after its launch from Earth, the OSIRIS-REx spacecraft finally attempted to collect its sample. The spacecraft descended toward Nightingale Crater, its cameras recording the approaching terrain. The descent proceeded exactly as planned, with the guidance system maintaining precise control of the spacecraft's position and orientation. As the spacecraft descended into the narrow crater, its solar panels passed within meters of the jagged crater walls, but cleared them successfully. The spacecraft continued to descend until the TAGSAM collection head was positioned just above the asteroid's surface. At this point, the collection sequence was initiated. The TAGSAM head made contact with Bennu's surface, and the pressurized nitrogen gas was expelled downward. However, something unexpected happened at this moment. The surface of Bennu did not behave like solid rock. Instead, it behaved more like a fluid. The contact of the TAGSAM with the surface created almost no resistance. The collection head, which was designed to touch down gently and retreat within a second or two, suddenly sank deeply into the surface, nearly half a meter into the loose material. The nitrogen gas blast, designed to be a brief pulse that would fluidize a thin layer of surface material, instead encountered a surface that was already partly in a fluid state. The blast proved extraordinarily effective, perhaps more effective than the designers had anticipated. A massive cloud of dust and small rocks erupted upward from the surface, engulfing the spacecraft. The collection head, designed to catch falling material, suddenly found itself inundated with a torrent of dust and rubble. The chambers designed to hold the collected material rapidly filled to capacity. The entire operation lasted less than 6 seconds, even briefer than the planned sequence. As soon as the collection head had gathered a substantial amount of material, the space thrust fired, pushing the spacecraft away from the surface and initiating the ascent out of Nightingale Crater. The spacecraft climbed slowly upward, carefully backing away from the jagged crater walls, until it had gained enough altitude to safely maneuver away from Bennu entirely. However, there was a complication. When the collection team examined telemetry from the spacecraft after the collection attempt, they discovered that the sample collection container, the chamber that was supposed to hold the collected material, filled so rapidly with material that it could not close properly. Rocks and dust were wedged in the sealing mechanism, and some of the precious sample material was leaking out into the vacuum of space, drifting away from the spacecraft. This was a crisis situation. The mission had collected far more material than anticipated, but at risk of losing a significant portion of it. However, the spacecraft's engineers quickly devised a solution. By carefully maneuvering the spacecraft and using specialized procedures, they were able to physically dislodge the rocks and debris that were preventing the container from sealing. Once the container could be sealed, the remaining material was secured inside. A significant amount of material had been lost, but a substantial portion of the sample successfully retained on the spacecraft. In the end, despite the complications and unexpected behavior of Bennu's surface, the OSIRIS-REx spacecraft successfully collected a sample from asteroid Bennu. Measurements indicated that the collection container held approximately 250 grams of material more than the minimum amount required for the mission's scientific objectives. The mission had achieved its primary goal. Now the challenge became getting that sample back to Earth safely, and then analyzing it to extract scientific insights that justified the entire elaborate undertaking. The return journey after collecting the sample, the OSIRIS-REx spacecraft still faced the task of returning to Earth. The spacecraft in orbit around Bennu for several additional months, performing final observations and taking additional scientific measurements. Eventually, in May 2021, the spacecraft performed a series of engine burns that altered its trajectory, placing it on a course that would eventually lead back to Earth. However, the journey home was not a direct route. The spacecraft could not simply point toward Earth and accelerate in that direction. The celestial mechanics of interplanetary travel are governed by orbital dynamics and gravitational fields. The most fuel-efficient path for the OSIRIS-REx spacecraft involved performing a complex maneuver that would use Earth's gravity as a gravitational assist. The spacecraft would pass near Earth at a specific velocity and direction, and the planet's gravity would bend the spacecraft's trajectory, redirecting it and slowing it down from its solar orbit to a velocity that would allow it to be captured by Earth's gravity and enter the atmosphere for landing. This journey, like the outbound trip to Bennu, required considerable time. The spacecraft traveled through space for approximately 2 years on its return journey. During this time, the spacecraft maintained proper orientation control, protecting the sample collection container and keeping the spacecraft systems in good working order. Scientists and engineers on Earth monitored the spacecraft's status constantly, ensuring that no problems developed that might jeopardize the sample or the spacecraft's ability to return safely. The actual return to Earth was scheduled for September 2023. As the spacecraft approached Earth, mission controllers worked to ensure that the re-entry sequence would proceed correctly. The sample collection capsule was equipped with a heat shield designed to protect the precious cargo during the intense heating that occurs when an object enters Earth's atmosphere from space. A spacecraft traveling at the speeds necessary from an asteroid near Earth's orbit enters the atmosphere at speeds of several kilometers per second. The extreme friction with the air creates temperatures on the outside of the heat shield that exceed 1,500 degrees Celsius. On September 24, 2023, the OSIRIS-REx sample return capsule separated from the rest of the spacecraft and began its final descent through Earth's atmosphere. The capsule's heat shield glowed brilliantly as it plummeted toward Earth, creating a spectacular meteor-like sight visible across the western United States. Parachutes deployed to slow the descent capsule toward a landing site in the Utah desert. The capsule touched down safely, and recovery teams were dispatched to retrieve it. When the capsule was opened in a specially prepared cleanroom facility at NASA's Johnson Space Center in Houston, scientists and mission team members finally got a first direct look at the material that the spacecraft had collected from Bennu. The sample consisted of a mixture of dust, sand, and small rocks, exactly what would be expected from the fluidized surface of a rubble pile asteroid. This material had spent billions of years on Bennu, undisturbed and unaltered. It had never passed through Earth's atmosphere. It had never been exposed to weathering or contamination by terrestrial life. For the first time, scientists had a pristine sample of carbonaceous asteroid material suitable for intensive laboratory analysis. Presolar grains. Windows into stellar depth. The analysis of the Bennu samples began immediately after the sample capsule reached the Johnson Space Center. Scientists from around the world prepared detailed analytical plans, identifying specific scientific questions that the samples might help answer. The analysis proceeded on multiple fronts simultaneously, with different teams investigating different aspects of the sample material. One of the most significant discoveries came from the analysis of presolar grains, microscopic crystals that formed in the outer layers of dying stars billions of years ago, long before our sun was born. These grains had drifted through interstellar space for millions or billions of years, before eventually being into the material that formed the asteroid that became Bennu. Presolar grains are extraordinarily rare in meteorites collected on Earth. In a typical carbonaceous chondrite meteorite, presolar grains make up only a few parts per million mass, a tiny fraction. However, scientists analyzing the Bennu samples found something remarkable. The samples contained an unusually high abundance of presolar grains. More remarkably, many of these presolar grains were composed of silicon carbide, a mineral that is extremely rare in terrestrial samples, but common in the stellar winds and outflows from certain types of stars, particularly asymptotic giant branch stars and supernovae. Silicon carbide is a hard, refractory mineral that resists breaking down under conditions that would destroy other minerals. Once formed in the hot outer layers of a dying star, silicon carbide grains can survive the journey through interstellar space and resist alteration by most chemical processes. The identification of these presolar grains came down to isotopic analysis. An isotope is a variant of an atom with a different number of neutrons than the standard form. While the number of protons in an atom determines which elements all carbon atoms have 6 protons, the number of neutrons can vary. An atom of carbon can have 6, 7, or 8 neutrons, resulting in carbon-12, carbon-13, or carbon-14. Different isotopes of the same element have slightly different properties, and they are produced in different nuclear processes. In our solar system, the ratio of carbon-12 to carbon-13 is essentially constant throughout all objects. This ratio reflects the mixture of materials that went into the original solar nebula. However, when scientists use mass spectrometry to analyze the carbon and silicon isotopes in the carbide grains from the Bennu samples, they found something astounding. The isotopic ratios in these grains were wildly different from the solar system average. Some grains showed extreme enrichments in carbon-3. Others showed different patterns. Crucially, these isotopic patterns did not match what would be expected from solar system chemistry. Instead, they matched the isotopic signatures would be produced by specific nuclear fusion processes that occur in the cores and outer layers of dying stars. By analyzing the specific isotopic patterns, scientists could actually identify the types of stars that produced these grains. Some of the grains had isotopic signatures consistent with production in asymptotic branch stars evolved, dying stars that have exhausted their core hydrogen fuel and are losing mass in their final stages of existence. Other grains had isotopic patterns consistent with production in type 2 and supernovae, the violent explosions of massive stars at the ends of their lives. This discovery was profound. It meant that the Bennu samples contained microscopic pieces of material that had been forged in the nuclear furnace of a dying star. These grains were literally made of the ashes of stellar death. They had then drifted through the darkness of interstellar space for an unknown period, waiting in absolute cold and silence. Eventually, they were swept into the collapsing cloud of gas and dust that would become our solar system. They were incorporated into the rocky material that eventually formed the asteroids. They had somehow survived all of this, ending up intact and unaltered inside the asteroid that became Bennu. The abundance of these presolar grains in the Bennu samples, compared to the rarity of presolar grains in meteorites from terrestrial collections, suggested something important. The population of meteorites that falls to Earth might not be a representative sample of all asteroid types. The meteorites we collect on Earth might be biased toward material that is more robust and resistant to damage during atmospheric entry. The more fragile, pristine material might be underrepresented in terrestrial meteorite collections. Bennu, by contrast, preserved a sample more closely represents the actual composition of the early solar nebula, including a higher proportion of fragile presolar material. The high concentration of presolar grains from stellar sources also provided clues about where in the solar nebula the asteroid that became Bennu originally formed. The solar nebula was not homogeneous. Different regions contained different mixtures of materials. A pristine snowfield might be covered with ash and soot from a nearby fire, but an area far from the fire would remain clean and white. Similarly, different regions of the solar nebula were enriched or depleted in Presolar grains, depending on where stellar material had been injected into the nebula. The high abundance of Presolar grains in Bennu suggests that this asteroid formed in a region of the solar nebula that had been recently polluted by material from a nearby stellar, possibly a supernova. This supernova explosion injected grains into the solar nebula, and the young asteroid captured these grains as it formed. This discovery suggests that our solar system did not form in complete isolation. Rather, nearby stellar events, the deaths of neighboring stars, played a role in determining the composition and characteristics of the solar nebula. The Presolar grains from Bennu provide direct evidence of this cosmic connection. Organic chemistry and the space gum, while the discovery of Presolar grains provided a window into stellar chemistry and the death of distant stars, other analyses of the Bennu samples revealed something equally remarkable: evidence of complex organic chemistry occurring in a small asteroid in space. The analysis of organic material in the samples began with routine procedures designed to extract and characterize carbon compounds. Scientists fully expected to find carbon in the Bennu samples. Carbon is one of the most abundant elements in the universe, and carbonaceous asteroids are specifically defined by their high carbon content. However, the nature and complexity of the organic material found in the Bennu samples exceeded expectations. Scattered throughout the sample material were strange, distinct globules of organic matter. These were not uniform, crystalline minerals. Instead, they appeared to be amorphous, pliable material organic polymers. NASA scientists, examining the samples under high-resolution electron microscopes, described this material as space gum because of its apparent texture and consistency. Unlike the hard, brittle mineral crystals that made up the bulk of the sample, these organic globules appeared to be soft, somewhat pliable, and distinct from the surrounding mineral matrix. When scientists analyzed the chemical composition of these organic globules, they found that they contained not just carbon and hydrogen, but also significant quantities of nitrogen and oxygen. This compositional complexity was important. Simple organic molecules like methane or other simple hydrocarbons contain only carbon and hydrogen. But when oxygen and nitrogen are incorporated into organic structures, the chemical possibilities become much more diverse and complex. Nitrogen and oxygen enable the formation of different types of chemical bonds and functional groups. Most importantly, nitrogen and oxygen are essential elements for the chemistry of life. Further analysis of the organic material revealed the presence of specific chemical compounds that are directly relevant to biological chemistry. The researchers identified amino acids, the fundamental building blocks from which proteins are constructed. Amino acids are organic molecules that cells use as the raw materials for building proteins, which perform virtually every function in living organisms. The presence of amino acids in the Bennu samples was remarkable because amino acids are so directly and intimately connected with biology. Every protein in every organism on Earth is made from amino acids linked together in specific sequences. The discoveries did not stop with amino acids. The scientists also detected the presence of sugars in the Bennu samples. Specifically, they identified glucose, the most common simple sugar and the basic fuel molecule that powers most cellular life. Even more significantly, They detected the presence of ribose, a 5-carbon sugar that is a crucial component of ribonucleic acid, or RNA. RNA is widely believed to be an ancient form of genetic material, potentially preceding DNA in the evolutionary history of life. The RNA world hypothesis, which is accepted by many scientists, suggests that the first cells evolved. Self-replicating RNA molecules dominated the primordial environment, essentially serving as a form of primitive life. The detection of ribose in the Bennu samples was a remarkable finding, because ribose is so specifically and intimately connected with genetic chemistry. The backbone of RNA molecules consists linked ribose in RNA or deoxyribose in DNA sugar molecules. The fact that this specific sugar, the crucial component of what many scientists believe was the earliest form of genetic material, was present in asteroidal, suggested something profound about the universe's chemistry. The analyses also revealed the presence of specific mineral phases that contained phosphorus in a bioavailable form. On Earth, phosphorus is essential for life. All organisms require phosphorus as a component in ATP, the energy currency of cells, and numerous other biological molecules. However, phos is often difficult to access in usable forms. Much of Earth's phosphorus is locked up in relatively insoluble minerals like apatite, which do not easily dissolve in water, and are therefore not readily available to organisms. The Bennu samples contained magnesium sodium phosphate, a phosphate mineral that has a crucial advantage over many other phosphate minerals. It is soluble in water. It dissolves readily when exposed to liquid water. This is precisely the type of phosphate that early life would have needed. Simple abiotic chemistry operating in the early solar system would not have produced primarily soluble phosphates. Insoluble phosphates are actually thermodynamically favored in many chemical reactions. The presence of soluble phosphates in the Bennu samples suggests chemical processes that preferentially generated bioavailable forms of phosphorus. The paradox of wet and dry discoveries from the Bennu samples created a fascinating geological paradox. On one hand, the presence of the organic polymers, amino acids, sugars, and soluble phosphates suggested that the parent body of Bennu had experienced significant interaction with liquid water. These complex organic molecules and the chemical transformations that produce them require the medium of liquid water to occur. The minerals comprising the bulk of the Bennu sample included phyllosilicates clay minerals that are specifically products of aqueous alteration, the process by which phyllosilicated minerals are converted to clay through interaction with liquid water. The vast majority of the Bennu sample consisted of these clay minerals, indicating that the parent asteroid had undergone extensive aqueous alteration. At some point in its history, water had flowed through the cracks and pores of the rock, facilitating chemical reactions that transformed the mineral assemblages and interacted with carbon compounds to produce the complex organic material that persisted in the sample. On the other hand, the sample also contained the Presolar grains, the delicate silicon carbide crystals, and other remnants of stellar material. These grains are extraordinarily fragile in the presence of hot water. If silicon carbide grains are exposed to a hydrothermal environment for extended periods, the water and dissolved minerals will cause the grains to oxidize and break down. The carbon in silicon carbide will be oxidized to form carbonic acid or other carbon oxides, while the silicon will potentially be converted to silica or silicates. Over the course of millions of years in a wet, reactive environment, presolar grains should be completely destroyed. Finding pristine, unaltered presolar grains that have maintained their original isotopic compositions and physical structures inside a rock that was clearly once wet is physically paradoxical. This paradox is equivalent to finding an intact ice cube sitting inside a pot of boiling water. The two conditions should be fundamentally incompatible. Yet the evidence in the Bennu samples clearly indicated that both conditions had existed in the same asteroid. The resolution to this paradox lies in the structural complexity of the Bennu samples themselves. When scientists examined the samples under high magnification, they discovered that the material was not uniform, while the background mineral matrix showed clear evidence of aqueous alteration and contained most of the minerals and complex organic material. There were distinct chunks of material embedded within this altered matrix that looked completely different. These chunks, called clasts, showed no evidence of aqueous alteration. They appeared to be fragments of material that had escaped the water interaction process entirely. These clasts are xenolith foreign rocks. The term xenolith literally means foreign stone. These are fragments of rock that have been incorporated into a different rock body, often as a result of collision or other geological events. The xenoliths in the Bennu samples appear to be pieces of material that originated from a different source than the altered clay-rich matrix. The leading interpretation is that these xenoliths represent material from a dry, unaltered source, possibly from an impactor asteroid or from the outer, unaltered layers of the parent body before collision mixed the materials together. The scenario that best explains the observations goes something like this. In the early solar system, there was a collision between two different asteroids or planetesimals. One of these bodies was wet, had experienced aquealteration, contained hydrated minerals, and had undergone complex organic chemistry. The other, unaltered, and contained delicate presolar grains preserved in their original state. The collision was violent, fragmenting both bodies. The debris from both bodies was ejected into space, but then gradually reaccumulated under mutual gravity to form a new rubble pile asteroid Bennu. In this reassembly process, material from both bodies was mixed together. Chunks from the wet, altered parent body were juxtaposed with fragments from the dry, pristine impactor. The result was a geological mosaic, a brexia composed of fragments from two different sources, each with distinct chemical and mineralogical characteristics. The clasts from the dry source were sealed inside the matrix material from the wet source. They were protected from the vacuum of space by the surrounding material. They were protected from further interaction with water by their isolation within the mineral matrix. The delicate presolar grains within these clasts were therefore shielded, preserved intact through all subsequent events. This interpretation explains how the apparent paradox could be resolved. It shows how both the evidence of aqueous alteration and the pristine presolar grains could coexist in the same asteroid. It also suggests that the early solar system was a chaotic, violent environment where collisions and mixing of material from different sources were common events. Implications for solar system formation. The discoveries from the Bennu samples have profound implications for our understanding of how the solar system formed and evolved. The presence of presolar grains indicates that our solar system did not form in complete isolation from the rest of the galaxy. Nearby stellar events, the deaths of neighboring stars, injected material into the cloud of gas and dust that eventually collapsed to form our sun and planets. This means that our solar system literally inherited material from the stellar neighborhood in which it formed. The recognition that the region of the solar nebula, where Bennu formed, was enriched in Presolar grains from supernovae suggests that the asteroid formed in a region that was directly influenced by stellar explosions. This has profound implications for the chemical composition and characteristics of the early solar system. The injection of supernova material into the solar nebula would have altered the local chemical composition, potentially triggering the collapse of the gas cloud or influencing the subsequent chemical reactions and processes that led to planet formation. The discovery also suggests that presolar grain abundances vary significantly across different regions of the solar nebula. The higher abundance of presolar grains in Bennu compared to typical meteorites implies that different parts of the solar nebula had different compositions and different histories of interaction with stellar material. This heterogeneity in the solar nebula has important implications for understanding how planets acquired their distinctive characteristics. Different regions of the solar nebula contained different mixtures of materials, and the location where a planet formed would influence its composition and properties. Implications for the origin of life beyond the insights into solar system formation. The organic discoveries from the Bennu samples have profound implications for understanding the origin of life. For many years, scientists debated whether the complex organic molecules necessary for life, amino acids, nucleotide bases, sugars, and other biological building blocks, were unearthed by some combination of atmospheric and chemical processes, or whether they were delivered to Earth from space via meteorites and asteroids. The Bennu samples provide strong evidence that a significant fraction of these building blocks are actually produced in space, in asteroids and other bodies throughout the solar system. The presence of amino acids, sugars, and other prebiotic organic molecules in asteroid material that had never been exposed to Earth's atmosphere or biosphere, that these molecules form through purely abiotic chemical processes operating in solar system material. Furthermore, the detection of ribose, the specific sugar that forms the backbone of RNA in Bennu material, suggests that the chemical processes occurring in asteroids are not random. The universe's organic chemistry actually preferentially produces molecules that are directly relevant to biology. This hints at something profound. The chemistry of the universe may be inherently biophilic, predisposed toward producing the molecules necessary for life. This would suggest that the origin of life is not a miraculous accident that happened to occur on Earth by an astronomically improbable chain of random events, but rather a natural consequence of the universe's fundamental chemistry. The presence of bioavailable phosphate in the Bennu samples also has important implications. Phosphorus is one of the rarest elements necessary for life, and bioavailable phosphate is even rarer. The discovery that asteroids contain soluble phosphates, exactly the form of phosphorus that early life would have needed, suggests that asteroids may have been important sources of phosphorus for the early Earth. The bombardment of Earth by asteroids during the first few million years of solar system history would have delivered not just raw chemical elements, but ready-made biological building blocks, and even some of the specific forms of those elements that would be most useful for life. The implications are striking. The molecules that comprise the genetic code and the molecules that power cellular metabolism appear to be not unique products of Earth's special conditions, but rather natural products of solar system chemistry. that occurred throughout the asteroid belt and other regions of space. This suggests that the chemical precursors to life are widespread throughout the solar system and potentially throughout the universe. The rubble pile, early solar system dynamics. The discovery that Bennu is a rubble pile asteroid with very low density raises interesting questions about the formation and evolution of asteroids in the early solar system. Rubble pile asteroids, probably not primordial objects that have remained unchanged since the solar system's formation. Instead, probably represent secondary assemblage collections of fragments that have been reassembled through gravitational attraction after being disrupted by collisions. The fact that Bennu is a rubble pile with approximately 50% void space, that it is an extremely fragile object. As previously mentioned, even modest increases in rotational velocity would cause it to fly apart. This raises questions about how such objects form and why they persist. The leading theory is that rubble piles form through collisions in the asteroid belt or in other regions of the solar system. When two asteroids collide at moderate velocities, they are often disrupted into fragments. These fragments are initially scattered, but if they don't have sufficient velocity to escape from each other's gravity, they will gradually reaccumulate through a process that can take years or decades. The reaccumulation occurs with little preferential alignment or compaction of the fragments. The result is a loose, porous structure, a rubble pile. The existence of rubble pile asteroids like Bennu has important implications for understanding the collisional history of the early solar system. It suggests that significant collisional activity occurred, disrupting and fragmenting asteroids. The reassembly of these fragments into rubble piles means that the composition and structure of an asteroid may be complex, reflecting contributions from multiple sources following collisions and reassembly. This is exactly what the Bennu samples suggest. Material from different sources, wet, altered material, pristine material, mixed together following a collision, then reassembled into a rubble pile structure. The broader context: returning samples from space. The OSIRIS mission represents much more than a single scientific investigation. It marks a crucial milestone in the history of planetary exploration. For most of the space age, human knowledge of the solar system came from remote sensing from instruments aboard spacecraft that observed objects from a distance. These observations were incredibly valuable and have enabled tremendous scientific progress. However, remote sensing has fundamental limitations. Instruments operating millions of miles away can only make measurements at low resolution and with limited precision. The analysis that can be performed on data transmitted through the radio link is constrained. Sample return missions, by contrast, allow scientists to bring physical material back to Earth, where it can be studied in sophisticated laboratory settings with instruments of extraordinary precision and sensitivity. Sophisticated techniques can be applied sequentially, and complex analyses can be performed that would be impossible to do robotically. Scientists can follow lines of inquiry as new results suggest directions for investigation. The material can be stored and studied for decades or even centuries as new analytical techniques are developed. The history of sample return missions demonstrates their scientific value. The Apollo missions sent 802 kilograms of lunar material from the moon in 1969 and 972. The study of these lunar samples over the past 5 decades has fundamentally transformed our understanding of the Moon's geology, its thermal history, and the broader history of the inner solar system. Decades after the material was collected, new analytical techniques and new scientific questions led scientists back to study the same samples, extracting new insights. The Bennu samples will almost certainly follow a similar trajectory. Scientists are currently studying the material intensively. But decades from now, new questions may inspire new analyses of these samples, uncovering insights that were not apparent to current researchers. The Soviet Union also conducted sample return missions, including the Luna missions that returned small amounts of lunar material, and the Phobos missions that were designed, though not fully successful, to return samples from the Martian moon Phobos. Japan's Hayabusa missions returned samples from asteroids Itokawa and Ryugu. These missions, along with OSIRIS-REx, demonstrate that sample return is becoming an established tool in planetary exploration. Looking forward, sample return missions are planned or proposed for numerous targets. Mars. The Mars Sample Return Mission will eventually return material collected by the Perseverance rover. Venus, Europa, Jupiter's icy moon, and other bodies in the solar system. Each of these missions will bring back physical material that will provide insights into conditions on other worlds and the history of the solar system. The OSIRIS-REx mission and its successful return of Bennu samples provide a precedent and a proof of concept for this approach to planetary exploration. Technical innovation and engineering achievement. While the scientific value of the Bennu samples is the primary justification for the OSIRIS-REx mission, the engineering and technical achievements of the spacecraft deserve recognition in their own right. Designing and building a spacecraft that could travel to a distant asteroid, collect samples under uncertain conditions, and return them to Earth safely required innovations in numerous areas of aerospace engineering and robotics. The TAGSAM collection head represented an innovative approach to sample collection in the low-gravity environment of an asteroid. The use of compressed nitrogen gas to fluidize surface material, rather than relying on mechanical excavation, showed sophisticated understanding of the physics of granular material and the unique properties of the asteroid environment. The mechanism had to be robust enough to function reliably over many years in the harsh environment of space, yet delicate enough to collect samples without destroying the fragile material that was the target of collection. The spacecraft's navigation system required extraordinary precision. The spacecraft had to approach and orbit a small object hundreds of meters in diameter at a distance of millions of miles from Earth. The guidance system used optical navigation, identifying stars and surface features to determine the spacecraft's position and orientation. This system had to maintain accuracy sufficient to safely approach the asteroid, enter orbit around it, hover at specified altitudes above the surface, and then depart safely. The margin for error was tiny. A significant navigation error could result in the spacecraft missing the asteroid entirely or crashing into it at high speed. The design of the spacecraft also required careful consideration of power generation and thermal control. The solar panels had to generate sufficient electrical power to operate the spacecraft and its instrument millions of miles from the Sun, where solar intensity is much lower than on Earth. The thermal design had to maintain appropriate operating temperatures for the spacecraft and its instruments despite the extreme cold of space and the varying amounts of solar heating as the spacecraft's orientation changed. The spacecraft had to be designed and tested to operate reliably over a 7-year mission with minimal opportunity for maintenance or repair. Every system had to have redundancy and fail-safe design. If a critical system failed, there had to be backup systems that could take over. The engineers and scientists had to think through potential problems and design mitigations before the spacecraft was launched. There would be no opportunity to fix problems after launch without the spacecraft having built-in redundancy and backup capabilities. Scientific analysis and future prospects. The initial analyses of the Bennu samples have been extraordinarily productive, but these analyses represent only the beginning of the scientific study of this material. The samples will continue to be studied intensively in the coming years and decades as scientists develop new questions and apply new analytical techniques to the material. The Presolar grain studies will continue to provide insights into stellar nucleosynthesis and the chemical processes that occur in dying stars. Different types of Presolar grains record different nucleosynthetic processes, and careful analysis of isotopic ratios and grain compositions can provide information about the characteristics of the parent stars. By collecting together the information from multiple Presolar grains with different isotopic signatures, can build a more complete picture of the stellar environments that influenced the early solar system. The organic chemistry studies will continue to investigate the pathways by which complex organic molecules form in asteroids. Laboratory experiments can simulate the conditions that existed in Bennu's parent body, and scientists can attempt to replicate the chemical reactions that produced the organic molecules observed in the samples. These experiments will help illuminate the processes by which the building blocks of life are produced through purely abiotic chemistry in the solar system. The mineralogical analysis, the clay minerals, and other alteration products will continue to provide information about the temperature, pressure, and composition of the fluids that caused aqueous alteration in Bennu's parent body. By understanding the conditions under which these minerals formed, scientists can constrain the thermal history and the environment within the parent asteroid billions of years ago. As new analytical techniques are developed, scientists will return to these new samples with new questions. Advanced isotopic techniques may allow determination of more precise ages for various components of the sample. New microscopic techniques may reveal details of grain structures that were not apparent with current instruments. New chemical analysis techniques may identify previously undetected compounds or trace elements. The samples represent a virtually unlimited resource for scientific investigation. Broader implications for human understanding, the OSIRIS-REx mission, and the analysis of the Bennu samples, implications that extend far beyond planetary science, and the specific questions about the early solar system. The mission represents a statement about human capability and human curiosity. It demonstrates that humanity has the technological sophistication to design and build machines capable of traveling to distant worlds, interacting with those worlds intelligently, and bringing back samples for careful study. The discoveries from the Bennu samples contribute to a broader understanding of humanity's place in the cosmos. The presence of the building blocks of life in asteroid material, preserved unchanged for billions of years, suggests that life itself may be a natural product of the universe's chemistry, rather than a miraculous accident. The recognition that our Sun is connected to stellar explosions that occurred billions of years ago, and that material from these explosions shaped the composition of the solar system, emphasizes the fundamental unity of the universe. We are connected to the stars not just metaphorically, but literally through the material that comprises our bodies and our planet. The study of presolar grains provides a perspective that spans billions of years and immense distances. A single grain of silicon carbide in a sample from Bennu connects us to a star that lived and died before our Sun was even born. It traveled through interstellar space, was incorporated into the solar nebula, became part of an asteroid, and waited in the darkness for billions of years until a species made of the same stellar material built a machine to find it. This grain connects past and present, Earth and space, the timescale of stellar evolution, and the timescale of human history. Conclusion: a window into the past, a guide to the future. The OSIRIS-REx mission and the analysis of the Bennu samples represent a significant milestone in humanity's effort to understand the cosmos and our place within it. The mission successfully brought back pristine samples of asteroid material that has never been exposed to Earth's atmosphere, never been altered by planetary processes, and never been contaminated by terrestrial life. These samples provide direct evidence about conditions in the early solar system and the chemical processes that occurred billions of years ago. The discovery of presolar grains in high abundance demonstrated that the early solar system was influenced by stellar explosions, and the materials composing the solar system were not produced entirely by the collapse of an isolated cloud of gas and dust. The nearby supernova that enriched the solar nebula in presolar material played a role in shaping the chemical composition of the system that eventually produced planets, and on at least one of those planets, life. The discovery of complex organic molecules, amino acids, and bioavailable phosphate in asteroid material suggests that the chemical building blocks of life are natural products of solar system chemistry, not unique creations of Earth's special conditions. This has profound implications for understanding the origin of life and the likelihood that life may have emerged in similar environments on other worlds. The rubble pile structure of Bennu and the evidence of collisional mixing and reassembly provides insights into the violent, dynamic environment of the early solar system. The solar system was not a quiet, orderly place in its youth. Instead, it was a chaotic region. Fragmentation and reassembly were common. This violence may have played an important role in mixing materials from different sources and distributing material throughout the solar system. Looking forward, the OSIRIS-REx mission establishes sample return as a crucial tool for planetary exploration. Future missions will bring back material from Mars, Venus, and other bodies, extending humanity's ability to study the solar system through direct physical samples rather than remote sensing alone. Each mission will return material that can be studied for decades or even centuries, continuously yielding new insights as analytical techniques improve and scientific questions evolve. The single grain of presolar silicon carbide dust that traveled through space for billions of years, survived a stellar explosion, crossed interstellar distances, became part of an asteroid, was incorporated in way darkness for cons, and was finally collected by a robotic spacecraft and brought home exemplifies what the OSIRIS-REx mission so remarkable. It represents the triumph of human curiosity, engineering capability, and determination to understand the universe. In that single grain, the entire history of matter in our region of the galaxy is encoded. By carefully studying material like this, brought back through extraordinary scientific and technical effort, humanity gains deeper understanding of the cosmos and our connection to it.